Welcome back to the problem for finding the exactly 3 devices. So let me give you a clarity of what this problem is about. For example, if I pass input as 6, I should get output as 1. Why should I get output as 1? There is only one divisor 4 which has exactly 3 devices. For example, what are the divisors of 4? 1, 2 and 4 itself, right? Similarly, for I is equal to 10, I should get output as 2 because the devices are 4 and 9. 4 we have already seen, but for 9 if you take, it's 1, 3 and 9. So this is what we need to return, the number of devices, the numbers of devices or numbers that have exactly 3 devices less than this input number. So now that we know this 4 and 9, what are the devices, could you get any kind of correlation between this? If you see, all the number starts with 1, correct? And then it has a prime number, in this case 2 and 3. And if you see the third device, they are all squares of it. So 4 and then 9. So whenever there is a perfect square within this range, which is less than number, then we can say that that perfect square have exactly 3 devices, like 4 and 9 over here. These are perfect squares, meaning 2 square, 3 square, right? Especially perfect square is nothing but it's the prime number square. For example, take the case of 25, right? 25 as well, 1, and it is divisible by 5, and then 25, right? 5 square, 25. Okay, so hence we say 5 is also perfect square. So perfect square is nothing but the prime number square. So now it's clear, right, what we need to do. So we just need to run a loop from 2 till square root of n, and if it is prime, then we have the perfect square. How can I say, like, if it's a prime we can say it's a perfect square? Because we are running this loop only till square root of n, which means whatever the square roots or prime numbers which we are finding within the square root of n, they're gonna have a perfect square. So that's the reason. Okay, cool. So let's try to write this program. So let me write. So basically let me create a new file, 14. Okay, 3 devices .js. Okay, let me create a function called exactly 3 devices, and then we will get the num, and inside this we need to make use of the is prime, right? So let's go here and we will copy this function because we need to know whether a number is prime or not. Let's not recreate it because we have already done so, right? And now since we are here, first thing we need to do is like let count is equal to 0 because we are just initializing the count. Now what we will do is like we'll run a loop from for let I is equal to 2, and then it will run till I times I. This is what I meant by square root of n less than or equal to num and then I plus plus. Inside this loop what we will do is like we will check if is prime of I. If that is the case, then we will do count plus plus, and in the end we will just return the count. Okay, so let's add some console log. So console log exactly 3 devices, and what are the test cases? Let me see. Yeah, first let's add a test case exactly 3 devices of 6, and we are expecting it to be 1, and the next case is 10, and let's add one more case, something like 25. Okay, great. So now if we try to run this program, node 14 3 devices.js, we get the output as we have 1 for 6, which is correct, and then we have exactly 3 devices. 10 for 10 it is 2, and then for 25 it is 3. For 25 it is 3, right? How it is 3? So basically the numbers that can be come inside the square root of 25 is 1, 2, 3, 4, 5. 1 is not a prime number, so leave it. So if you see, 2 is a prime number, correct? And 3 is a prime number, and 4 is not a prime number, 5 is a prime number, and hence we get the output as 3. So all the prime number squares is the output. Great. So this is the solution for getting the exactly 3 devices. Basically the idea is to get the perfect squares. Perfect square is nothing but prime number squared. Okay, prime number squared has only 3 devices. That's the idea. Great, thank you. And before that, one more thing, the time complexity of this approach is basically, if you see this code, prime number is going to take how much? Square root of n, right? And here we are also running another loop till square root. It's kind of like big O of n power 1 by 2 into 1 by 2, I guess, probably, yeah, n by 2, n power 1 by 2 into n power 1 by 2. So that is the time complexity. In auxiliary space, it's big O of 1. Okay, so it's big O of n power 1 by 2 into n power 1 by 2, because here as well we are doing an I into I, and here as well, inside as well, we will do a same operation. So that's big O of n power 1 by 2 into n power 1 by 2 for time complexity, and we just use one variable count and nothing other than that. So it's big O of 1 for space complexity. Okay, thank you.